Hey kids, welcome back to Mr. Murray's Mathland here. Just doing a little review today of properties of exponents, multiplying, dividing, zero exponents, negative exponents, and some exponential growth and decay word problems. So hitting a little bit of everything here. Just even starting with basic numbers here. 2 squared times 2 to the third. Now I used a number example because you have the luxury of being able to actually evaluate it and check these properties and make sure you trust them, because you know that 2 squared is 4 and 2 cubed is 8. So the answer we're coming up with here is really 4 times 8, or 32. But what we're really after here are these properties with common bases having exponents and how we multiply those things. And to do that, just remember 2 squared really means 2 times 2 times 2 to the third, which is really 2 times 2 times 2. So when you put that all together, what do you really have? You have 5 2's, or 2 to the fifth. And that should just bring up this idea that you should know that when you multiply two things with the same base, having exponents, you keep that same base and you add their exponents, right? I don't get 4 to the fifth, like sometimes people get a little confused. It's 2 to the fifth, because that's all you're really doing is counting up those total number of 2's. And yes, 2 to the fifth is 32, of course. So when you get to x to the third times x to the fourth, you know, I could not add these variables because they're not like terms, but I can multiply them, common base. That's just really, again, if you wanted to write it out the first time till you trust it, x to the third is really just 3 x's. Times x to the fourth, that's really just 4 more x's. So what do I really have? Just the product of 7 x's in a row. So it's x to the seventh. And of course that's 3 plus 4. Boom. So you get to these where they've got coefficients and more than one variable. Piece of cake, right? You multiply coefficients by coefficients. Negative 2 times 7, negative 14. A to the fifth times a squared. You do your common bases by common bases. A to the fifth times a squared is a to the 5 plus 2 is 7. And b times b to the 8th is b to the, remember there's an unwritten exponent of 1 there, so 1 plus the 8 that are there give you 9 b's altogether. Negative 14, a to the 7th, b to the 9th. Very good. Okay. Now, moving along, what about when we raise expressions with exponents to exponents? So powers raised to powers, as we say. So very easy. Raising this to the fourth power would really mean writing it out 4 times, and I don't feel like I have to do that right now. You should feel pretty good. This is a review after all. Now what you're really doing is 4 raised to the fourth. You do have to raise everything in here to the fourth power, and since this is a review, I'm going to write it out. X to the 8th to the fourth, y to the third to the fourth. So I'm going to apply that power 4 to everything in there. Now 4 to the fourth, that's a number there. That's 4 squared is 16, and times another 4. So 4 to the fourth is 256. Check your calculator if you don't believe me. But it's about these powers raised to a power. That's what I really want to talk about. X to the 8th to the fourth. If you were going to do that out by hand, it would be x to the 8th times x to the 8th times x to the 8th times x to the 8th. So you'd really just be adding up those exponents of 8 plus 8 plus 8 plus 8. Or in other words, the shortcut, just multiply them, right? X to the 8th to the fourth will give you x to the 32. Y cubed to the fourth, you multiply when you're doing power to a power and you get y to the 12th. And there we go. Right here, just another example here. Keep in mind that that is a coefficient of -1, so you're doing -1 to the 10th, w to the 6th to the 10th, z cubed to the 10th. And the important thing here, a negative number raised to an even exponent will always be positive, right? -1 to the 10th power is going to be -1, -1, -1, and there's an even number of negatives, so negative times negative is positive, so you're going to get positive 1. And I don't need to write positive 1 as a coefficient. It's implied. So that's good there. That's just 1. W to the 6th to the 10th, that's going to give you W to the 60th. Z cubed to the 10th, Z to the 30th. And like I said, I don't need to write that coefficient of 1 there. It's kind of redundant. when you're a professional algebra student such as yourselves. And now we're going to raise all this to the third power. Piece of cake here, negative 2 to the third, and x to the 0 to the third. We'll talk about that in a moment. Negative 2 to the third. Now we have a negative number to an odd power. Keep in mind when you raise a negative to an odd power, you get a negative number because that's negative 2 times negative 2, which is positive 4, but then times negative 2 again. So it switches it back to being negative. Whenever there's an odd exponent, a negative to odd is negative, and 2 cubed is 8. Now x to the 0 to the third, if you strictly use this rule of the multiplying, then you get x to the 0. But what you should know is we don't leave that in a final answer. What is anything to the 0 except 0? X to the 0 is equal to 1, you might recall. And one way to refresh yourself on that will actually be, if you want to remember why that is, here's one way to convince yourself. If you have x to the 5th divided by x to the 5th, now this is going to use the division rule we get to in just a second here, but when you divide, it's the opposite of multiplication, so you subtract your exponents. 5 minus 5 is 0. And what does this equal? Well, it came from dividing this by itself, and anything divided by itself, 7 divided by 7, 8 divided by 8, 200 divided by 200 is always 1. So that's kind of maybe not exactly the proof, but it should be the convincing argument of why x to the 0 or anything to the 0 is 1, except 0 to the 0. That is undefined. Okay, so now we alluded to it just there, but let's talk about dividing and dealing with negative exponents, which are going to pop up from time to time. A couple ways to think about this. One way is to just go and divide and use that subtraction rule for any of the exponents. Now 18 divided by 24, those are coefficients. Those are numbers that are being divided, so you're not subtracting those. 18 divided by 24 does reduce to 3/4. Okay, now here's one way to go about handling the variables. You just x divided by x, I'm going to subtract their exponents. X to the 8th divided by x squared is x to the 6th. And notice where I'm putting it. It goes up top if you're using this subtraction rule. Y to the 3rd divided by y to the 5th gives you y to the, and 3 minus 5 is negative 2. Now one thing you might remember is that we never leave a negative exponent in a final answer, so I'm going to move that to the denominator. Negative exponents, remember, do not make negative answers. They make reciprocals. So that's really 1 over y squared, which just moves that to the bottom. And the other way to approach this, as some of you may have thought, is just, hey, it's just reducing a fraction. I don't need to subtract the exponents, that's just 3/4. X to the 8th, x squared. There's 2 in the bottom and 8 up top, so that means I'm going to be left with 6 x's in the top. Y to the 3rd over y to the 5th. There's more in the bottom than the top, so all 3 of these are going to cancel, and you're going to be left with 2 y's in the bottom. So just whatever way you go about it, don't confuse yourself, be clear. A lot of you, I remember, like the subtraction rule, so remember, if you do the subtraction rule, everything in that first subtraction step starts up top, and then if it has a negative exponent, you move it to the bottom. All right, so here we go. We got a bunch of x's together here, so I'm going to do a couple little simplifying steps. First thing I might do is maybe multiply these together. They're a common base, x and x. So x to the negative 2nd times x to the negative 3rd is x to the, we add their exponents when we multiply, and that will be x to the negative 5th. Okay, and now let's divide. 6 divided by 2 is 3. X to the negative 5th divided by x, again, that's an unwritten 1 there, is x to the negative 5 minus 1, negative 6. Not going to leave that as a final answer. Going to move that negative exponent, but keep in mind the 3 doesn't have the negative exponent, only the x does. So I'm going to keep the 3 right up top and move x to the bottom, 3 over x to the 6th. And a lot of you might be saying, I could have spotted that back here really. If you saw this with the negative exponent, you could have moved it to the bottom and put x to the 5th along with the x and made x to the 6th in the bottom. So more than one way to kind of approach these, but you're doing all the same stuff. So just don't, confuse yourself and do two of them and kind of put it back to the top. All right, moving along here. Just a few more examples with negative exponents because they are a little tricky. If you have just a regular old number here, 6 to the negative second, that would be 1 over 6 squared. Again, it doesn't make negative 36 or anything. It makes 1 over 36. Right? They make reciprocals, not negative numbers. And you can think about it if you like in short form. I won't go through the long thing we did in class, but if you do 6 squared, you're multiplying 6 times 6. That's what exponents are about, multiplication. Well, when you do negatives, that's really dividing, the opposite of multiplication. So you're really dividing by 6 times 6, which is why you end up getting that. So maybe that makes it stick with you a little bit better too. And, just another example here, you've got some combos. 2 times negative 5, negative 10. A to the negative 6 times a squared is a to the, add their exponents. Negative 6 plus 2 is negative 4. B squared times b is b to the third, right? 2 plus that 1. And you're going to leave that? No, of course you're not. I know you're shaking your head right now at home. But this has the negative exponent, the a, so that is the term that's going to move. So negative 10b to the third stays right up top, but this is really 1 over a to the fourth, so we move that to the denominator and put it all over a to the positive fourth. And what about this? What about when you've got an entire fraction raised to a negative exponent? There's a few ways you could handle this. You could apply the negative 2 exponent to everything in there and then move any negative exponents that you're left with. Or you could do this. Look, if it's all raised to negative 2 and negatives just make reciprocals, I could just make a giant reciprocal. So move everything in the bottom to the top, move everything in the top to the bottom, giant reciprocal, and then make the power positive 2, right? Because that's all you really do. And now I'll raise everything to the second. Although you could start on the inside and simplify your x's first if you like to. Does not matter. Hey, maybe I'll square everything though. 3 squared gives you 9. X to the 6th squared is x to the 12th, right? Power to a power, we multiply. 5 squared is 25. Don't tell me it's 10, that's 5 times 2. X to the negative 5th squared is x to the negative 10th. That's the multiplication, power raised to power. And now here, you definitely are seeing there's something that needs to be done, and one way to go about it, x to the 12th divided by x to the negative 10th is x to the 12 minus negative 10. Watch that double negative, you're really adding, and you get 22. So you have 9x to the 22nd over 25. And that's done. Good. Or you could think about it just like taking this and moving it to the top and making 22 up there. Whatever you like. Okay, and then what would it be without a couple word problems just to show you how these can be applied, just at least in a couple ways. So here we go. We have a viral video. Yeah, just keeping it topical for you kids. A TikTok video of a dabbing baby going viral. Today the video has 280 views, but the number of views is increasing by 78% each hour. How many views will this video have after 2 days? So there's a lot of little things to pay attention here. Let's start with the basic increase function here. So the amount after time t, or population after time t, whatever you want to call this. If you want to just write y equals, that's fine. But the basic setup, remember, for this was, your initial amount, and in this case it's 280, and this could be applied to a lot of banking problems, population growth, in this case the growth of this video views, and then to incorporate this 78%, it's increasing by that amount each hour. So we always start with 1, and if it's increasing we would use a plus, and 78% as a decimal is 0.78, remember, of course, right? To the left, right? A little Beyonce style. 0.78, right? Raised to the t. And it's 1, remember, that 1 is in there, so it's, if I want to simplify this, that's 1.78. 1 is in there because that's the 280 if you were to distribute. 280 plus the 78% of 280 you'd be gaining. So this kind of does it all in one step, rather than having to find the percent growth and then add it back on to itself, right? 280 times 1 plus that percentage growth. And so there's your function in simplified form. So if I want to know what's after 2 days, hopefully you would catch this, that these are not the same unit. 2 days, this is set up in terms of hours. Well, then you just have to know that each day is 24 hours, so 2 days is 48 hours. I'm sorry if you think that's unfair. And so I really want to know, well, what is the amount of use that this will have after 48 hours? So 280 times 1.78 raised to the 48. And let's see, and then we'll round to the nearest whole number since we're talking about views. This one I'm not doing in my head. 280 times 1 plus the 78% growth raised to the 48. Wow, that is scientific notation there. That's what your calculator is trying to tell you when it gives you E something. That means times 10 to the. So I'll round this to the nearest number here, I guess, nearest whole number, but it's in scientific notation anyway. So that would be, well, I guess I'll call it 2.9 times 10 to the 14th. So that would be like moving the decimal 14 places to the right. So pretty large number there. And that's what happens with exponential growth. You know, you talk about these curves growing and flattening and all that. Exponential growth takes off very sharply. And last one here, a little Chromebook here. Sorry if this is hitting too close to home. The value of your Chromebook decreases by 8.5% each month after its purchase. If the Chromebook was initially purchased for $200, how much is it worth after the 10-month school year? And I know you're probably saying, well, mine is worth 0 because I broke it a long time ago and I'll have to pay for it. But let's assume this was a responsible kid and they still have it. It still loses some value each month, and that's why this number is on average. So very similar approach. The amount, the value of this, if you want to use V of t, it was 200 initially and then 1, but we're decreasing, so we're losing, we're taking away that percent each month in this case. And again, 8.5, use that correct decimal version for that, and that is 0.085, right? 8.5 means 8 out of 100, so that would be 8 in the hundredths place, right? Just like 8 cents on a price tag, 8%, right? 0.08. And you don't have to simplify this, but I always like to. 1 minus 0.085, and no surprise that that equals 0.915, which should make sense because if you take away 8.5% of its value each month, that means what you're keeping, what you're left with, is 91.5% of its value from the previous month, and that's what that decimal represents. So that's why I always like to simplify and talk about it for a minute. And so how much will this be worth after 10 of these, 10 months of decreasing at this percent? We plug in 10 to the exponent, and again, doing that on my calculator, and you get about 82.27. Since we're talking about money, we'll round to the nearest cent, so about 82.27, $82.27. Not too bad after 1 year, but hey, pretty soon it's gonna go down. And if it keeps going, does its value ever get to 0? If you keep taking away a percent of it, it goes down and down and down, but will it ever get down to 0 mathematically? Not really. It'll get there, if you take away half of a penny, you're left with half of a penny, and half of that is a quarter of a penny. So you'll practically get to 0 in terms of the real world nature. But mathematically, you never would really get to 0, and the reason I mention that is if you remember these graphs, this was an exponential decay, And it would be going like that, never quite getting to 0, because there's what we call a horizontal asymptote. And all exponential graphs have that in some way, that invisible ceiling or barrier that it's going to get super, super close to but never get to. So anyway, a little extra icing there on the cake, if you're still listening, that is. So have a good day. Enjoy the exponential problems you have. And if you have any questions, just ask. See you later.